To finish up Unit 9, what we need to review now is some more stoichiometry, but in the context of solutions. So that means we're going to have to do some mole to mole conversions or some gram to mole or some variation of stoichiometry, but we're going to sprinkle in a couple equations from the solutions unit. And most specifically, that's going to be your molarity problems. So we'll be doing a little bit of molarity, molarity equal moles over liters, and some good old stoichiometry. All right, so what I have right here, of course, is I have my solubility rules on the left side of the screen and then the note packet on the right side of the screen, and you'll see why I have that up, because we're going to need it. So number one, it says calculate the concentration of some volume of sulfuric acid that reacts with excess barium chloride. Again, don't worry about the word excess. And it forms some amount of precipitate. Now, they don't tell us what the precipitate is, so that's why I'm going to need the solubility rules on the left side of the page. The first thing we need to do, of course, is come up with the balanced chemical equation. So it says that we have sulfuric acid, H2SO4. It is going to react with barium chloride, BaCl2, because barium has a +2 charge. And it's going to make, at least we know we're going to make one precipitate. Now, remember, this is a double replacement. So I'm going to go ahead and switch the metals on the front. So I'm going to put the H, not with the SO4, but with the Cl. And I'm going to take the Ba and put it with the SO4. Now, H and Cl both have a +1, -1, so it's just HCl. Ba is a +2, SO4 is a -2, so those cancel out. So it's really just HCl plus BaSO4. To balance this, I have two H's on the sulfuric acid and I have two H's on the barium chloride. So I just need a 2 there, and we have a balanced chemical equation for the reaction between sulfuric acid and barium chloride. Now, because we have a precipitate that is formed and we don't know which one it is, it's going to be one of these two, but, well, which one? So what we need to do is use our solubility rules. I'm going to go ahead and go with the first one. Chlorine is right here behind that little dot. Again, it's bound to hydrogen. Hydrogen is not one of these exceptions. So this would be aqueous and soluble. All right, then let's go ahead and check the other one. By the process of elimination, it's probably that one, right? Barium sulfate. So sulfate, again, is right here. We'll look at the exceptions. It's bound to barium. Barium is an exception, therefore it is going to be insoluble. This is our precipitate. We know, again, using the solubility rules, that barium sulfate is the precipitate we're looking for. Now, going back to the question, what we have, of course, is we have 2.5 grams of precipitate. What precipitate? Barium sulfate. Again, because we found that by the solubility rules. So what I'm going to do is I'm going to put the mass of barium sulfate down here from the periodic table called molar mass, and I'm going to convert into moles of barium sulfate. Okay, what we want to solve for is calculate the concentration of sulfuric acid. So we need to get out of barium sulfate and into moles of sulfuric acid, H2SO4. Okay, so the first one, we have moles over grams. Moles is always 1. The grams comes from the periodic table. The mass of barium sulfate is 233.38 grams. And then over here on the right side, we have moles over moles. You guys know this comes from the balanced chemical equation. For sulfuric acid, there's nothing in the front right here, so that's a 1. On the bottom, barium sulfate, there's nothing in the front over there either. That's also going to be a 1. So 1-to-1 ratio. So what we're going to do is we're going to go ahead and calculate this out. I already have the answer, so it's going to be 0.0107 moles of sulfuric acid. Okay, so what we've done, again, is we've started with the mass of the precipitate. Once we determined what the precipitate is, then we converted out of mass of barium sulfate into moles of the precipitate, of the sulfuric acid. So what we need to do now is we need to use our molarity equation because they want us to calculate the concentration. So I'm going to go ahead and say that concentration is molarity, same thing. Well, molarity is a numerical measurement of concentration, to be correct. My moles are going to go up here, and then my volume is going to go down here. Now, My volume is 250 milliliters. Again, that's the same thing as 0.025 liters. Again, why? Because I'm moving the decimal 3 spots to the left. So I'm going to go ahead and just put that here, 0.025 liters. So my molarity, once we get this all solved, is going to be 0.428 molar of sulfuric acid. So that's the final answer there. Again, I think I misspoke earlier, so let me go ahead and repeat myself. What we had to do is get the 2.5 grams of precipitate. Once we determined that the precipitate was barium sulfate, we converted into moles of sulfuric acid. Why sulfuric acid? Because that is what they are asking for. Calculate the concentration of sulfuric acid. That's why we went to sulfuric acid. Once we had the moles and we had the volume, we just needed to convert that into liters, do the simple molarity calculation, and we got our answer in molarity of sulfuric acid. So again, this took quite a bit. We had to predict the products. We had to determine which of the products was insoluble. Then we had to do a little bit of stoichiometry. And finally, we had to do the new part, which is the molarity. So let's go ahead and move on to the next one. All right, number 2. What we have here is, again, we need to figure out what is the equation. We're going to have lead 2 nitrate, lead 2 Pb with a +2 charge. Nitrate is NO3 with a -1 charge. So the 2 of the lead will go back here. It's going to react with, that's a plus sign, lithium chloride, LiCl. Li is +1, Cl is -1, and they're going to react. So we need to figure out what it is. We do know that, again, the lead and the lithium will switch places. So I'm going to put Pb, Cl2, why 2? Because the lead is a +2 charge. That is also going to produce LiNO3. Li is a +1, NO3 is a -1, so therefore it's just LiNO3. So that is our chemical equation. I almost said balanced, it's not balanced. NO3, I have 2 in the lead 2 nitrate, so I need a 2 there. That gives me 2 nitrates, but that also gives me 2 lithiums. So I put 2 there, then I have 2 lithiums, but it also gives me 2 chlorines. Well, it's okay because I have 2 chlorines on the right, so we are now balanced. Again, we do need to make sure we have this balanced correctly because we need to do the stoichiometry, and we're going to need to be able to have a balanced chemical equation for our mole ratio, right? So back to the question. 171 milliliters of a 0.45 molar lead 2 nitrate aqueous solution reacts with 2.25 molar lithium chloride. What volume in milliliters of the lithium chloride solution is needed to react completely with the lead 2 nitrate? Now, this sounds really complicated. What I'm going to go ahead and do is start with what we have for the lead 2 nitrate. So we know that our molarity is 0.450 molar. And then that's going to be moles over liters. Now remember, 171 milliliters is the same thing as 0.71 liters. 0.171 liters. When I solve that, X is going to be equal to 0.76 moles of what? Of lead 2 nitrate. Okay. So what we've done is we have got used our molarity. So we're kind of the opposite of number 1, right? We're starting with the molarity portion first because we needed to get into moles of lead 2 nitrate. Now that we have moles of lead 2 nitrate, we're going to go ahead and use that number. So 0.76 moles of lead 2 nitrate. I write kind of small. And we're going to convert out of that into our moles of what we want. What do we want? We want lithium. What volume of lithium chloride? We want lithium chloride. That's what we're trying to solve for. So once we have that, let's go ahead and, So when we have moles over moles, of course, in the bottom, we have PbNO3. In the front, we have nothing, so that's a 1. Over here for lithium chloride, there's a 2 in the front, so that is a 2. So when we multiply this number by 2, we're going to get 0.154 moles of lithium chloride. Okay, so we just converted from moles of lead-2 nitrate into moles of lithium chloride. Now, the last thing I want us to do, another step, is what volume in milliliters of the lithium chloride solution is needed. So what we need to do now is our molarity. So we know that molarity is right here. 2.25 molar solution is equal to 0.154 moles of lithium chloride over some unknown volume in liters. Again, you guys know, just as a shortcut, when the X is on the bottom, all I have to do is switch these two, and that will mathematically and algebraically be a legitimate move. So I'm just going to do 0.154 divided by 2.25. And what we're going to get as our answer, I'm running out of space here, as you guys can tell, is going to be 0.06844. Now, the reason why I'm writing so many numbers is you're going to see here in a second. That is liters. They want us to put it in milliliters, so I need to move my decimal. Again, 1, 2, 3 spots to the right. So it's going to be 68.44 milliliters. All right, that's quite a bit of an advanced question, right? Again, we were given everything we need for our lead-2 nitrate. So we did the molarity calculation first to get into moles of lead-2 nitrate. Once we did that, we converted out of lead-2 nitrate and into lithium chloride because that is the compound they want us to solve for, to solve the volume for. Once we had our moles of lithium chloride, we used the molarity of lithium chloride provided to us in the question, and we converted into the volume of lithium chloride and then converted that into milliliters, which is what they want, 68.44 milliliters. Again, that's quite a bit more thinking than was required on number 1. But again, if you do this stepwise, just look at what you have, what you need, understand that you're going to need at least one molarity calculation and of course some stoichiometry, then I know you guys can get there. Let's go ahead and try number 3. Number 3. All right, so we have some volume of a molarity of silver nitrate. Silver nitrate is AgNO3, is added to sodium chloride, which is good old table salt, NaCl, yielding a precipitate. Okay, we don't know what that precipitate is yet, but we're gonna have to figure it out. Again, I'm gonna take the silver and the sodium and swap them. So I'm gonna put sodium nitrate, NaNO3. Na is a +1 and nitrate is a -1, so that works out quite nicely. And then my Ag will go on front of the Cl. Ag is a +1, Cl is a -1. Again, very generous. These compounds are really easy to solve for. It is already balanced. Everything is 1. We have 1 of everything, so it is already balanced. It's a 1 to 1 to 1 to 1 ratio. All right, going back to the question, what we have here is we have 20 milliliters of a 1.5 molar silver nitrate. So that's for silver nitrate, this. Are added to another volume at another molarity of sodium chloride, of that, yielding a precipitate. Calculate the number of grams of precipitate formed. First of all, let's go ahead and figure out what is the precipitate. Is it sodium nitrate or is it silver chloride? I don't know. Sodium nitrate, nitrate is located right over here. There are no exceptions. Therefore, this has to be aqueous, AQ. Sorry guys, little squiggles, sorry about that. The next thing again is we have to figure out what about the other one. Again, process elimination, it's probably silver chloride. Chloride is right here. Look at the exceptions. There is silver. Silver is an exception, therefore it becomes insoluble. So that is our precipitate. We need to figure that out because we need to figure out what are we solving for. Now back to the question. We're given a volume and a molarity for both of our starting reactants, the silver nitrate and the sodium chloride. So we're going to have to figure out which of these is the limiting reactant. You guys remember this from last semester. The limiting reactant is the one that would produce the least amount of product. Now, what we could do is go from convert both of those into moles using the molarity calculation, which we're going to do here in a second. And then we could go all the way into mass of silver chloride. We're not going to need to do that. And the reason is because this equation is a 1 to 1 to 1 to 1 ratio. because it's nice and it's a 1 all the way across the board, all we really need to do is see which one has the least number of moles. Whichever has the least numbers of moles would also produce the least amount of silver chloride. If the equation was a 2 to 1 to 2 to or 3 to 6 or some other variation of a balanced equation, then we would really need to go all the way to grams to figure out how many grams of silver chloride would be produced. But let's go ahead and try the silver chloride first. So my silver chloride, I'm going to do that over here. My molarity is 0.150 molarity. Again, this is right here. Is equal to some number of moles over, again, this is equal to 0.020 liters, 0.020 liters. And then when I solve that, again, all I need to do is multiply those two numbers together. And what I get is 0.003 moles of AgNO3. Okay, I'm gonna do the same thing, but for the silver chloride over here. Again, all my numbers for the silver chloride are located here. So I'm gonna go ahead and put my molarity, which is 0.200 molar, equals some number of moles over, again, this would equal 0.030 liters, 0.030 liters. Multiply those two together, and what I'm gonna get is 0.006 moles of sodium chloride. All right, knowing what we know now, again, as I said a little bit ago, the reaction is a 1 to 1 to 1 to 1 ratio. Therefore, we do not need to go all the way to mass of silver chloride to see which one would make the least, excuse me. All we need to do is look at these two numbers we have here, the number of moles of our two reactants. And as you guys can see, this is the smaller one. Therefore, our limiting reactant of what we have less of is the silver nitrate. So we can assume now that the silver nitrate will be consumed first because we have twice as much sodium chloride. Again, that's easy because it's a 1 to 1 to 1 to 1 ratio. Like I said several times before, but just to repeat, if the reaction was not 1 all the way across, we would need to convert those into grams of silver chloride, our precipitate, to see which one would make the least, okay? What we're gonna do now is we're gonna start with this mass, or this number of moles, 0.003 moles of silver nitrate. Again, why are we starting with this one? Because again, it's the smaller of the two. We're not gonna use this one because it's larger. The sodium chloride is going to be your excess reagent, and the silver nitrate is our limiting reagent or reactant. So I'm going to go put moles of silver nitrate here. We're going to put moles of our precipitate, AgCl, here. They want, again, the question's asking, calculate the number of grams. So we need one more step, moles of silver chloride, grams of silver chloride. That will get us to where we need to go. As you guys know, these should cancel. Otherwise, we've done it incorrectly, excuse me. When I have moles over moles, you guys know this comes from balanced chemical equation. Everything is 1, so it's a 1 to 1 ratio. On the right, moles underneath grams is going to be 1. Grams comes from the periodic table. If I add the mass of silver and chlorine together, I get 143.32 grams of silver chloride. All right, so all I need to do is do 0.003 times 143.432, excuse me. And what I get is 0.43 grams of silver chloride. There is our final answer. So to talk through this problem one more time, again, we were given two starting points. We were given a volume and a molarity for both reactants. You guys know from previous units that whenever they give you two starting points, that's going to be a limiting reactant problem. We had to start with both of those and convert them both into moles to determine which had the least. Because again, it's a 1 to 1 to 1 to 1 ratio. All we needed to figure out is what do we have less of. Whatever we have less of is going to be consumed first. The sodium chloride had double the amount of silver nitrate. Therefore, I was not concerned with the silver chloride. That was a dead end. My silver nitrate, once I got that into moles, I converted that into moles of our precipitate, which we determined using the solubility rules to be silver chloride. Once we got into moles of silver chloride, we just had to do one additional step to go into grams of silver chloride. And then we got our final answer of 0.43 grams of silver chloride. So like I said, guys, this is definitely not easy. We're going to do some basic stoichiometry as well as the molarity calculation. Again, on this one is a little bit harder because again, they gave us two starting points. We just had to figure out which is the one that was actually more relevant, which one would be the limiting reactant, because that is the one that will limit the amount of product formed, in this case, the silver chloride. All right, guys, I hope I didn't make your brains hurt. Thanks again for watching. If you guys have any questions, you guys know what to do. Ask me questions.